Hello and welcome. This is a video on integrals involving hyperbolic functions. Make sure you've already watched my two other videos on hyperbolic functions. There's one called Introduction to Hyperbolic Functions and also Derivatives of Hyperbolic Functions. You want to watch those in order and then watch this one last, because I will be referencing stuff that we learned in the other videos in this video. So now integrals involving hyperbolic functions are very useful. And we have lots of good formulas on that standard formula sheet. So on the formulas from Calculus 1 and Calculus 2, if you look on the first page, you got hyperbolic functions, that has all the derivatives. You have hyperbolic identities, we don't really use these that much. But then hyperbolic antiderivatives, that's what we're going to be focusing on here. Because remember, let me zoom in. Remember that antiderivatives are the same as integrals, okay? It's just they're indefinite integrals, so you write plus c at the end. And of course, the first one we're going to be focusing on is the integral of sinh of u du and the integral of cosh of u du. But remember that integrals and derivatives are inverse operations. So it makes sense that since the derivative of cosh of u is equal to sinh of u, that makes sense that the integral of sinh of u has to be cosh of u, because it's just the same thing in reverse. So these first two formulas are the easiest formulas. The integral of sinh equals cosh, and the integral of cosh equals sinh. So let's see an example of using these. Okay, that'll be our first example. Okay, so example, evaluate each integral. Evaluate each integral Okay, and for our first integral, we're going to be doing a pretty easy one. So number one is just going to be the integral of cosh of 5x dx. Okay, the integral of cosh of 5x dx. So notice that this one does not have any numbers that we're plugging in. So this is an indefinite integral, aka antiderivative. Okay, so indefinite integrals and antiderivatives are the same thing. So what we want to do is we want to write this in the form integral of cosh of u du, so that we can use the formula on the first page of the formula sheet. So in order to get it in the form integral of cosh of u du, we're going to have to let u be the inside of this composite function. Okay, so here we're going to let u be 5x. Okay, so u is going to equal 5x. And then taking the derivative, we get du dx equals 5. And then if you follow my method, I isolate dx and plug it back in. Okay, so here, if I multiply both sides by dx and divide both sides by 5, I get du over 5 equals dx. Okay, and then we're going to go ahead and replace that dx up here with du over 5. Okay, just like we do on any other composite function. Standard u substitution. So what we get here is the integral of cosh of u times du over 5, right? Because we said dx was the same as du over 5. All right, and then the 5 in the denominator can just be factored out front because it's a constant. So if we bring the 1/5 out front, then we're just going to have 1/5 times the integral of cosh of u du. One-fifth times the integral of cosh of u du. And as we were just saying, the integral of cosh is sinh, so this is going to be sinh of u. But because it's an indefinite integral, it doesn't have numbers that we're plugging in, we're going to have to write plus c at the end. So we're going to have 1/5 times sinh of u plus c. Okay, and you don't need to distribute the 1/5 to the c, because c over 5 is still a constant, so we would still call it c. So you only have the 1/5 times the sinh of u. But, technically this is what the integral is, but if you distribute the 1/5 to the c, it's still a constant, so you're still just going to call it c. Okay, so after we do that, we're going to end up with plugging back in the original expression in terms of u. We're going to have 1/5 times sinh of, well, originally we said in this problem u equals 5x. Okay, so we're going to plug back in 5x in for u there. Okay, so we're going to have sinh of 5x plus c. Okay, 1/5 sinh of 5x plus c. And one nice thing to notice when you're doing integrals is if you have a composite function and on the inside you just have a number times the variable, like this 5x, notice that you actually end up dividing by that constant in your answer. So notice that this 5 in front of the x actually ended up getting divided by in our answer. So the integral of cosh of 5x dx just ended up dividing by 5, and then we got sinh of 5x. Okay, so 1/5 sinh of 5x plus c. It's just cool to notice those patterns because sometimes it can save you a lot of time. Once you get the pattern on how integrals work, you don't have to write out every step like I do. Okay, so let's see another example. Okay, so example number 2. For this one, we have the integral of 3 sinh, of the quantity x over 2 minus ln of 2 dx. Okay, so the integral of 3 sinh of parentheses x over 2 minus ln of 2 dx. Okay, so this is actually a pretty easy one if you know what you're doing. So all you really have to do here is factor out the 3 since it's a constant. And then once again, because we have a composite function, we need to let u be the inside of this composite function. So in other words, u is going to be this big thing inside of sinh. Okay, so here our u is actually just going to be all of this. X over 2 minus ln of 2. Okay, so if we let u equal x over 2 minus ln of 2, then we need to go ahead and take the derivative. Okay, so we're going to get du dx equals, well, what's the derivative of x over 2? Well, that's the same as the derivative of 1/2 x, and you just get rid of the variable. So that's actually just going to be 1/2. And then what is the derivative of negative ln of 2? Well, remember that 2 is a constant, so that means ln of 2 is a constant, which means negative ln of 2 is also a constant. And the derivative of a constant is 0. Okay, so this one is actually going to be, that's going to become 0 in the derivative. Okay, so we actually just get du dx equals 1/2. And then if we isolate dx by cross multiplying here, if I multiply both sides by 2 and multiply both sides by dx, I get 2 du equals dx. And then we can go ahead and plug in 2 du in for dx up here in the original expression. Okay, so what's that going to give us? Well, now we're going to have, the 3 is going to be factored out front because that was just a constant. So we're going to have 3 times the integral. 3 times the integral of sinh, and we're doing sinh of, well, this whole thing is u. So let me erase this last one so I have more room. So it's going to be 3 times the integral of sinh of u, and then we're replacing dx with 2 du. Okay, so it's going to be 3 times the integral of sinh of u 2 du. Okay, and then just like 3, 2 is also a constant. Okay, so we can actually factor this 2 out front, and then we're going to be multiplying. 3 times 2 is 6 for the constants out front. So we're actually going to have 6 times the integral of sinh of u du. Okay, 6 times the integral of sinh of u du. And then what is the integral of sinh? It's just cosh. Okay, so the 6 stays out front. So we're going to get 6 times cosh of u plus c. Okay, and technically you can distribute the 6 to both of those terms, but 6 times c is still a constant, so we still just write c. We don't write 6c. We just write c. Because it's an arbitrary constant, it doesn't matter what's multiplied by it. It's just a constant. Okay, so here we're actually just going to get 6 times cosh of u plus c. But remember, u in this problem was actually x over 2 minus ln of 2. So we're going to have 6 times cosh of parentheses x over 2 minus ln of 2 plus c. Okay? So it's actually very similar to the last problem. It's just a little bit harder because it has fractions, and I thought some people might not know what to do with this negative ln of 2, but it's actually a constant, so that makes it a lot easier. Okay, so that's our answer. All right, cool. So that was number 2. So let's take a look at example number 3. Example number 3 is the integral of coth of x over 10, the integral of coth of x over 10 dx. Now, remember in my other video where I talked about the introduction to the hyperbolic functions, all of these functions, sinh, cosh, coth, these are all hyperbolic trig functions. They're technically not trigonometric functions, but some books call them trig functions. So they're just like sine, cosine, tangent, cotangent, but they have a little h there to show that they're hyperbolic. So here we want to do the integral of coth of x over 10 dx. So let's take a look at our formula sheet under hyperbolic antiderivatives. So on this first page, going to the last line at the top, we want to do the integral of coth. But we look here, and nowhere do we see a coth. So that's interesting. So nowhere do we see the integral of coth. We have a bunch of other stuff up here, but we don't have the integral of coth. So how on earth do we do this? You might be wondering. Well, even though we don't have a formula for it, we can still integrate it. Okay, but it is going to be a little bit trickier. So remember that we have identities involving hyperbolic functions. And the hyperbolic identities I wanted to show you are actually on the last page of our formula sheet. So I talked about these in an earlier video. But the one we want to use here is coth of x. So coth of x is actually equal to cosh of x over sinh of x. This is the one that we're going to be using here. And you'll see why I'm using it in just a second. Okay, so coth of x is cosh of x over sinh of x. So here, coth of x over 10 is going to be cosh of x over 10 over sinh of x over 10. Okay, and we're integrating this dx. And remember, if you remember your formulas from pre-calculus, cotangent is the same as cosine over sine. And here, coth is the same as cosh over sinh. So it has basically the exact same formula, it's just these are hyperbolic functions. Okay, so now you might be wondering, well, why did I decide to use this particular formula? How is it helpful for doing the integral? Well, what we can do here is we can actually let the denominator be u. And the reason I want to let the denominator be u is that's actually the most complicated composite function here. Okay, so I'm actually going to let this sinh of x over 10, that's actually going to be u. Alright, and it's just kind of a trick. Why am I doing that? Well, if I let the numerator be u, then how would I cancel stuff out in the denominator? That would be the problem. Whereas if I let the denominator be u, then we know that the derivative of sinh is cosh, so that means this cosh of x over 10 is actually going to end up canceling out, so that's why it's going to work out for us. Okay, so you kind of have to think ahead and be a little smart about it, or at least do trial and error until something works. Okay, so here we're going to let u equals sinh of x over 10. U equals sinh of x over 10. Okay, and then of course we take the derivative of both sides, so we get du dx equals, well, the derivative of sinh, the outer function, is cosh. So remember, in my last video I talked about the derivatives of hyperbolic functions. So they're here under hyperbolic functions. D dx of sinh of u is cosh of u times du dx. And also remember the derivative of cosh is sinh. So there's no minus with those. Okay, so the derivative of sinh here, du dx, is going to give us cosh of x over 10. Okay, so we have cosh of x over 10. And then, so that was taking the derivative of the outer function, inner left alone, and now we multiply this times the derivative of the inner function. So the inner function is actually x over 10. So what's the derivative of x over 10? Well, the variable goes away and we're just left with 1/10. So this is going to be cosh of x over 10 times 1/10. Okay? And then if you want to do it the way I teach it, the next step would be to isolate dx. Okay, so if we want to isolate dx here, we multiply both sides by dx, and then we multiply both sides by 10 and divide both sides by cosh of x over 10. Okay, so in other words, all of this here goes down to that denominator, and then the dx comes up over here. So what are we going to end up with? Well, we're going to have the 1/10 is going to get flipped over. And so now the 10 is going to be up on the top on the other side. Okay, so we're going to actually, on the left side, we're going to have 10 du. And then in the denominator, we're going to have cosh of x over 10. And then on the right side, now we should just have dx. Okay, so what I did there is I flipped over the 1/10, so it ended up being in the numerator on the left side. And then I also divided both sides by cosh of x of 10, so that ended up on the left side. And then I multiplied both sides by dx. Okay, so in other words, I was just isolating dx. That's what we did there. We isolated dx. Okay, but now that dx is isolated, even though it's kind of complicated looking, we can plug in this big thing here in for dx. And you're going to notice that stuff is going to cancel out because that cosh of x over 10 on the bottom is actually going to cancel out with this cosh of x over 10 up here, which is what we want. Okay, so what are we going to get here? We're going to have the integral of cosh of x over 10 divided by, well, remember, sinh of x over 10 is actually just u. So we're just going to have u in the denominator. And then plugging in for dx, we're actually going to be plugging in this right here. So 10 du over cosh of x over 10. Okay, so here we have 10 du over cosh of x over 10. So then the cosh of x over 10, those two things cancel out, which is what we wanted. And we can factor the 10 out front because that is a constant. Okay, so after we do that, we're going to wind up with 10 times the integral of 1 over u du. Okay, 10 times the integral of 1 over u du. All right, and what is the integral of 1 over u du? Well, if you forgot it, it's on your formula sheet. So you look under antiderivatives. The integral of 1 over u du is natural log of absolute value of u plus c. Okay, so this one is actually just going to be 10 times natural log of absolute value of u plus c. And I just like to write plus c at the end without distributing the 10 because 10 times c is still a constant. So it's still just going to be c. All right, and then of course we have to plug back in the original expression in terms of the original variable. So what did we say u was in this problem? Well, in this problem, u was actually sinh of x over 10. So we're going to plug that in for u at the end here. Okay, so we actually have 10 times natural log of absolute value of sinh of x over 10, okay, plus c. And that's actually how they left their answer. So that's all we have to do there. Okay, so this is going to be our full answer. Pretty cool, huh? I kind of like these. I don't know what you guys feel, but these are kind of fun for me. Okay, so let's continue onward. That was problem number 3. So let's go ahead and take a look at problem number 4. Okay, problem number 4 is the integral of, let me pull it up real fast. The integral of sec squared, of 2x minus 1/2 dx. Okay, the integral of sec squared of parentheses 2x minus 1/2 dx. So what we're looking for is a formula that has the integral of sec squared of u du. So let's see if we can find that. So interestingly enough, under hyperbolic antiderivatives, we just have the integral of sinh of u and the integral of cosh of u. But up here, I don't see any integral of sec squared. So what do we do? They don't have everything that you need on this formula sheet because there's just so much stuff that, you know, could be on here that isn't on here. But what we can do here is we can kind of work backwards. So if you look at this formula right here, d dx of tanh of u equals sec squared of u times du dx. If we look at this one in reverse, then it's actually saying the integral of sec squared of u du equals tanh of u. Okay, so important note, this isn't on our formula sheet, at least not directly. However, we do know that integrals and derivatives are inverse operations. So in particular, if we're looking at these derivatives here, we can see that the derivative of tanh of u is sec squared of u times du dx. Okay, so that's the one, that's going to be this little thing that we're going to use here. So d dx of tanh of u equals sec squared of u times du dx. Okay, and if you just realize that derivatives and integrals are inverse operations, if I integrate both sides of this equation, then I'm actually just going to end up with, on the left side, we're going to have tanh of u plus c equals the integral of sec squared of u du. Okay, so where did I get this formula from? I took this formula, which is on our formula sheet, and then I basically just integrated both sides, and I took advantage of the fact that derivatives, d dx, is the opposite of integrals. So if you integrate both sides here, you actually just get tanh of u plus c on the left side, and then on the right side, you get the integral of sec squared of u du. Okay, so those dx's actually just cancel out. Okay, so keep that in mind, that if you just have these formulas here, you can actually start on the right side and work to the left side, and that will be an integral. So that's the trick with those kinds of questions. Okay, so this is the formula we want to use here. Integral of sec squared of u du equals tanh of u plus c. Same exact formula as what's written up here. It's just if you integrate both sides, then you have the integral on the right side, and then you just have tanh of u plus c on the left side. Okay, so that's our formula. And then, so here we want to rewrite 2x minus 1/2 as u, because that's the inside of our composite function. So here, we're going to let 2x minus 1/2 be u. Okay, and then so u equals 2x minus 1/2. Okay, and then du dx is going to be the derivative of this. So du dx equals 2. Because the derivative of 2x is 2, and the derivative of a constant is 0, so this negative 1/2 just goes away. And then if we isolate dx here, multiply both sides by dx and divide both sides by 2, we get dx on the right side, and then on the left side we get du over 2. Okay, so we can go ahead and plug in du over 2 in for dx. Plug in du over 2 in for dx up here. Okay, so that's going to give us the integral of sec squared of u times du over 2. Okay, the integral of sec squared of u times du over 2. Okay, and then the du over 2 is the same as 1/2 du, so we can actually factor out that 1/2 out front since it's a constant. So if I bring out this 1/2, I'm going to get 1/2 times the integral of sec squared of u du. Okay, and what we were saying about that was it's really just, let me zoom in a little bit. It's really just this formula right here. I'll zoom in even more, just in case your video is blurry. So if you look at this formula here, d dx of tanh of u equals sec squared of u times du dx. Well, since derivatives and integrals are reverse operations, you can just start on the right side and integrate to get the left side. So this just means on the right side, integral of sec squared of u du equals the left side, which is tanh of u, and then you write plus c because it's an indefinite integral. Okay, so hopefully that makes sense. So here we're just going to get tanh of u plus c, but we also have a 1/2 out front. Okay, so now we have 1/2 times tanh of u plus c. And then all we have to do is plug back in whatever u was in this problem. So in this problem we said u was actually 2x minus 1/2. Okay, so we're going to have 1/2 times tanh of 2x minus 1/2 plus c. 1/2 times tanh of parentheses 2x minus 1/2 plus c. All right, and that's actually, I believe that's what they got as their answer on My Math Lab. Yeah, so that's how they wrote their answer, so we're good there. Pretty cool, huh? Okay, so the big trick there is that it isn't directly on the formula sheet, but it kind of is right there on the formula sheet. It's just you're going to have to look at the right side here. But if you integrate any of these functions on the right side, it brings you to the left side. So for example, if you end up in a problem where you have sec of u times tanh of u, and you need to integrate that, well, the integral of sec of u times tanh of u, if you put a minus in front of it, is just going to equal sec of u. So you can take advantage of that fact, and because that gives you a bunch more formulas here. You can start on the right side of any one of these, and then if you integrate it, that gets you to the left side. So I think that's pretty slick, though, that you can do that. One of the cool things about calculus. Okay, so that was problem number 4. And I think I wanted to do 2 more. So problem number 5 is a bit harder. So for problem number 5, it can look a little bit intimidating. We have the integral of sec of root 3t times tanh of root 3t all over root 3t, and then this whole thing is multiplied times dt. Okay, so the integral of sec of root 3t, tanh of root 3t, all over root 3t dt. Should probably zoom out a little bit so I can write it a little bit more neatly. Okay, because that's just a lot to write at once. Okay, so what we got here is something that looks a little bit intimidating, mostly because of the root 3t in the denominator. But like I was just saying, even though this formula doesn't show up directly on your formula sheet, it does show up under hyperbolic functions. It's just you're going to have to start on the right side to integrate it and get to the left side. So in particular, with this one, we have sec times tanh. So it's sec of u times tanh of u all over u. But this thing is going to end up canceling out, I believe. So we're just going to focus on, well, what is the integral of sec of u times tanh of u du? Because that's the formula we need that's not actually on our formula sheet. Okay, so note from your formula sheet. Well, we know that the derivative of sec of u equals negative sec of u tanh of u du dx. Okay, so d dx of sec of u equals negative sec of u tangent of u du dx. Okay. But then the problem with that is we need the integral, right? We actually need the integral of sec of u, tangent of u, du. And then the root 3t will get canceled out when we do the u substitution, so we're not going to worry about this right now. Okay, but just like with the last formula, if you integrate both sides of this, then your integral is going to be on the right side, and then on the left side, your derivative is going to cancel out. So what I'm trying to say here is if I integrate both sides dx, if I integrate both sides of this dx, the dx's cancel on the left side, and the dx's cancel on the right side. And on the left side, the d and the integral cancel out. And then because it's an indefinite integral, on the left side, you actually have a plus c. Okay, so on the left side, we're actually going to have sec of u plus c. And then on the right side, we have, if we bring the minus out front, if we factor this minus out front, we get negative integral of sec of u tangent of u du. Okay, so once again, even though it doesn't show up directly on our formula sheet, it is a formula that we can easily figure out by just starting on the right side and working to the left side. Okay, so the only thing that's a little bit weird here is we have a minus, okay? And in the original problem, we didn't have a minus. So one thing we can do here is, with this equation, we can just multiply both sides by -1. Okay, so if I multiply both sides by -1, if I multiply both sides by -1, on the left side, I'm going to have negative sec of u plus c. So if I switch this around, I'm going to have the integral of sec of u tangent of u du. So these minuses are going to cancel. And then on the other side, I'm going to have negative sec of u plus c. Okay, so there I went ahead and switched the order around just to make it easier to read. Okay, so all I did in that step was I multiplied both sides by -1, and then I switched the order of the formula. So this side went over here, and that side went over here. And notice, even though -1 was multiplied by c, c is just a constant. So you don't need to write negative c, because negative c is still just an arbitrary constant. So you just write plus c, no matter what. Okay, so this is the formula we want to use here. And if you're familiar with these, you might be able to just do them in your head, because really all we did with this formula is we started on the right side here and we worked the left side of this formula right here. But really the only difference is there's a minus here. So you just have to move the minus to the left side and then you've got the integral. So it's an important thing to realize that integrals, the primary thing that we're focusing on here that you need to remember is that integrals and derivatives are inverse functions. Okay, so if you're starting on the left side and going to the right side as a derivative, that's the same as starting on the right side and going to the left side as an integral. Okay, so integrals and derivatives are inverse operations. And that's why we're able to do this, where we start on the right side and go to the left side and get an integral formula out of it, when we started with a derivative formula. Okay, so anyway, this is the formula we're going to be using here, even though it's not directly on our formula sheet. And if you want to look these up, I'm sure they're up there somewhere online. They just didn't happen to make it onto my big formula sheet. But if you don't want to do what I'm doing here and think about it a lot, you can probably find derivatives and integrals of hyperbolic functions for a bigger formula sheet, and you can probably find one online. But this is what we're going to use here. So here, our u is going to have to be root 3t. Okay? So our u is actually going to be root 3t. So now what we've got here is, since u is going to be root 3t, so that we can get it in the form integral of sec of u, tan of u, du, we need to go ahead and do the u substitution. Okay, so over here, since u is actually going to equal root 3t, that's going to be the same idea as root 3 times root t. So root 3t is actually the same as root 3 times root t. Okay, and remember that the square root of t is the same as t to the 1/2 power. So this is the same as saying u equals root 3 times t to the 1/2 power. Okay, and then if we take the derivative of this, we're going to get du dt equals root 3 times, well, if I bring the 1/2 out front and decrease the exponent by 1, I'm going to get 1/2 times t to the negative 1/2. Okay, but remember t to the negative 1/2, if I move that down to the denominator, it's going to become t to the positive 1/2, which is the same as root t. Okay, so now I'm actually going to have my du dt. My du dt is going to be root 3 over 2 root t. Right? Because we have a root 3 on the top, we have a 2 on the bottom, and then moving this t to the negative 1/2 down to the denominator, it becomes t to the positive 1/2, which is the same as the square root of t. Okay? And then if you want to follow my method, then I'm just going to go ahead and isolate dt here. Okay, so isolate dt. At least that's the way I usually teach it. Even though it can look messy, stuff ends up canceling out at the end, so it's kind of a satisfying process. So to isolate dt here, we're going to have to cross multiply both sides by dt, and then multiply both sides by 2 root t, and then I'm also going to move this root 3 down to that denominator. Okay, so I'm going to get on the left side 2 root t du over root 3 equals dt. And if you can't do all that fraction stuff at once, you can also write it out in multiple steps. But the basic idea is this denominator is going over here, so that's how we got a 2 root t on the left side. This denominator went over to the right side, so we got a dt there. And then this numerator, this root 3, moved down here. So we're really just cross-multiplying. Okay, we're cross-multiplying and also dividing both sides by root 3. But now we've isolated dt, so we can plug in this huge mess here in for dt in the original problem. So we got 2 root t du over root 3, and we're going to plug that in for dt. And then you'll see a bunch of stuff is going to cancel out. Okay, so actually I'm going to go down here. So let me go ahead and erase all this stuff down here, since we already talked about that. That way I have some room to write down here. Okay, so plugging everything in here. Oops, what did I do? Oh, sorry, my computer's going slow for some reason. Okay, there we go. So what we got here is our original integral now is going to be the integral of sec of u, tan of u, right? Because we said root 3t is u. So we have integral of sech of u, tangent of u over root 3t times, well, what did we say dt was? dt is what I circled in green here. So it's going to be 2 root t du over root 3. 2 root t du over root 3. Okay? And that certainly is a lot of stuff going on there, but that's what we got. Because we multiplied both sides by 2 root t, we multiplied both sides by dt, and then we divided both sides by root 3. So that is correct. Okay, so the nice thing here is over here, we can rewrite this root 3t as root 3 times root t. And then we're going to be able to simplify this. So first of all, what you should notice is we have this root t up here and that root t down there. So those are going to cancel out. Okay, and then another thing you should notice is that we have root 3 times root 3. So a square root times itself is just the number on the inside. So in other words, those square roots cancel out and we get 3. Okay, so root 3 times root 3 is 3. So we're actually just going to have the integral of 2/3 times sech of u times tangent of u du. So how did I get 2/3? Well, these root t's canceled out, and then I have a 2 in the numerator, so I brought that out front. And then in the denominator, root 3 times root 3, the square roots cancel out, and you just get 3. And then, of course, 2/3 is a constant, so we can bring that outside of the integral. Okay, so I can actually write this as 2/3 times the integral of sech of u, tangent of u, du. And what did we say the integral of sech of u, tangent of u, du is? Well, I erased it down here, but I can still easily figure it out by just looking at these formulas. So the integral of sech of u, tangent of u is, if we move the minus to the other side, it's going to be negative sech of u plus c. Okay, that's just using this formula, moving the minus to the other side, and then we're done. Okay, so here we're going to have 2/3 times negative sech of u plus c. Okay, and then of course we have to plug back in the original expression for u. So in this problem, u was actually root 3t. Okay, and if we bring this minus out front, we're going to have negative 2/3 times sech of root 3t, since our u was root 3t, plus c. Right, because in this problem we said u is root 3t. Right, and believe it or not, that's exactly how my math lab wrote their answer. So we did all of that correctly. Yay! Okay, cool. So that's a harder problem, for sure. But hopefully it's not too bad. If you follow my video, then you'll be able to do your homework. Okay, now there's just one more that I wanted to do. We're only going to have one definite integral on our homework, and I wanted to do a similar example to it on here. So this is going to be example number 6. Let me zoom back in a little bit here. Well, that's too far. Okay, that should be fine. So for example number 6, we're going to be taking a look at our only definite integral on the homework. Okay, so for this one we're doing the integral from 0 to ln of 3 of tangent of x dx. The integral from 0 to ln of 3 of tangent of x dx. Now this is a definite integral because we're going to be plugging in 0 and ln of 3 at the end of the problem. But the rest of the problem is just going to be the same. We're only going to be plugging in numbers at the very end. Okay, and keep in mind that since the original variable here is x, this 0 and ln of 3, those are both x. Okay, so we're evaluating from x equals 0 to x equals ln of 3. Now, how are we going to do the integral of tanh of x dx? Well, if I look at these formulas, on the right side, none of them have tanh. I mean, this one has tanh, but there's a sech there, so that's not going to work. So what do? Well, actually, we're going to do the same thing we did with coth. So remember back up here earlier, we did coth. I think that was problem number 3. So what do we do with coth? Well, we wrote it as cosh over sinh. Okay, but now we're going to do the same thing. It's just now our function is tanh. So what is the formula for tanh? Well, just like with regular trig functions, tangent is sine over cosine. So tanh is sinh over cosh. And you can always check on here to make sure. So if I go to, let me zoom out. If I go to the page with your hyperbolic identities, that's on the last page, we can see that tanh of x is actually sinh of x over cosh of x. So that's that one right there. I don't know if you can see that. Let me zoom in. Tanh of x equals sinh of x over cosh of x. That's on the last page of your formula sheet. Okay, so right off the bat, we're going to go ahead and rewrite this as the integral of sinh of x over cosh of x dx. Okay, and again, if you want to kind of skip ahead, you can always go online and look for an exact formula. Like there will be exact formulas for the integral of tanh of x dx, but I wanted to show you how to do it without those formulas so that we can actually learn the math behind it. Okay? So what we're doing here is, once again, we want to let u be the inside of our composite function. And the composite function here is going to be 1 over cosh of x. So on this problem, we're going to let u be our denominator. Okay, so u is actually going to be cosh of x. So if u equals cosh of x, then taking the derivative, we get du dx equals sinh of x. Right? Because remember, with hyperbolic functions, if you go to your first page, derivatives of hyperbolic functions, the derivative of sinh is positive cosh, but the derivative of cosh is also positive sinh. So there's no minus there like there is with regular trig functions. Okay, so du dx is going to be sinh of x. And then if I isolate dx here, like I always do, divide both sides by sinh of x, I get du over sinh of x. And then I multiply both sides by dx. Then I'll be able to plug in du over sinh of x in for dx up here in the original problem. Okay, and that's going to work out because the sinh of x's are going to cancel out. All right, so now we're going to have the integral of sinh of x over u. Now, how do we get u here? Well, remember, we said that cosh of x is u. So we're going to go ahead and replace cosh of x with u. So we have the integral of sinh of x over u times, instead of dx, now we're going to have du over sinh of x. Okay, du over sinh of x. And of course, the fun thing about my approach where you isolate dx is that stuff cancels out now. So the sinh of x's cross out, and then everything simplifies, and we just wind up with the integral of 1 over u du. Okay, the integral of 1 over u du. All right, and we know that the integral of 1 over u is natural log of absolute value of u plus c. Natural log of absolute value of u plus c. However, I'm not going to write a plus c here because this one was a definite integral. Remember the original problem? We actually had numbers to plug in here, so we're going to be plugging those in at the end. So I'm just going to write natural log of absolute value of u, and then I'm going to plug back in, instead of u, we're going to have cosh of x. So this is going to be natural log of absolute value of cosh of x. Okay, and now that it's back in terms of x, I can go ahead and write the numbers that we started off with. So this is a definite integral, and the limits of integration that we're going to plug in are x equals 0 and x equals ln of 3. Okay, so this is going from x equals 0 to x equals ln of 3. All right, and remember, using the fundamental theorem of calculus part 2, you're just plugging in the top number into the function, and then you subtract the function evaluated at the bottom number. Okay, so let's go ahead and do that. So plugging in the top number, we have ln of absolute value of cosh of ln of 3 minus ln of absolute value of cosh of 0. Okay? So that's what we should have in this step. Now this is going to be your hardest problem on your homework, because for the rest of the problem, you're actually going to have to simplify it. So you might think, well, why do I have to simplify it? Why can't I just leave it this way? Well, remember from an earlier video when I talked about my introduction to hyperbolic functions, we said that cosh is actually, if you look on the first page, cosh of x is actually e to the x plus e to the negative x all over 2. So we can actually plug that in here. And then we can use that information to simplify this stuff. Okay, so over here, let me just write down, just in case you didn't watch the earlier video or you forgot. So recall from my earlier video, cosh of x equals e to the x plus e to the negative x all over 2. E to the x plus e to the negative x all over 2. And that's right here. On the first page of your formula sheet, cosh of x equals e to the x plus e to the negative x all over 2. So we can use that information here to simplify these. So in the first one, our x is going to be ln of 3, and then in the second one, our x is going to be 0. Okay, so plugging in here, I'm going to have ln of absolute value of, well, cosh of ln of 3 is going to be e to the ln of 3 plus e to the negative ln of 3 over 2. So all I did there was I replaced cosh of ln of 3 with this. E to the ln of 3 plus e to the negative ln of 3 all over 2. And that's just using this formula right here. Okay, and then we have minus ln of cosh of 0. Okay, so that's minus ln. Well, what's cosh of 0 going to be? Well, here our x is actually going to be 0. So using the same formula, we're going to get e to the 0 plus e to the negative 0 all over 2. Okay? And don't forget, we still have an ln of an absolute value around each of these. But now we can simplify these. Okay? So what can we do to simplify this? Well, for the first one, we can actually cancel out the e and the ln. So this e and this ln cancel out, and we just get 3. Okay, so we're going to have 3 plus, well, what about this one? This is the same as e to the negative ln of 3 to the negative 1 power. Okay, so what I'm saying is here, the e and the ln are also going to cancel out. The e and the ln are going to cancel out here as well. But we're going to have 3, and then we're going to have a negative 1 power. So it's not actually going to be negative 3. It's going to be 3 to the negative 1 power. Okay? And the reason it's not negative 3 is this up here was actually e to the ln of 3 raised to the negative 1 power. Okay, that's what that means when you have a minus as your exponent. All right, so that's just a little important detail. So we have ln of absolute value of 3 plus 3 to the negative 1 all over 2 minus ln of, well, what's any number to the 0? Any number to the 0 is just 1. So e to the 0 is just going to be 1, and e to the negative 0 is the same as e to the 0. That's also 1. Okay, so for the second one, we're going to have natural log of 1 plus 1 over 2. All right, now for the first one, the 3 to the negative 1, if we move that 3 to the denominator, that's going to become 1/3. Okay, so we have ln of absolute value of 3 plus 1/3 all over 2 minus ln of absolute value of 1 plus 1 is 2 over 2. Okay? And then what's 3 plus 1/3? Well, we can build these to a common denominator. Remember, 3 is the same as 9/3, right? Multiplying the top and the bottom by 3, so they have a common denominator. And then adding, we're going to have 9/3 plus 1/3 is 10/3. Okay, so we're going to have ln of absolute value of 10/3 divided by 2 minus ln of absolute value of 1. Now for 10/3 divided by 2, 10 divided by 2 is 5. Okay, so we can cross out that 10 and that 2, and we get a 5/3. We're left with 5/3. All right, so what we have is ln of absolute value of 5/3 minus ln of absolute value of 1. But remember that the absolute value of a positive number is just the number. So since both of these numbers are positive, we don't actually need this absolute value. So we're just going to have ln of 5/3 minus ln of 1. Okay? And then to get to the answer that they got on MyMathLab, the only thing you need to simplify here is ln of 1. So what is ln of 1? Well, it's the same as asking yourself, e to what power gives me 1? Well, we know that e to the 0 is 1. So this ln of 1 is actually just simplifying to 0. Okay, so this is 0. And why is that true? Well, it's log base e of 1, which is the same as e to what power gives me 1? Well, e to the 0 gives me 1, so ln of 1 is 0. All right, so that brings us to our final answer, which is ln of 5/3. Okay? And that's the exact answer they got on MyMathLab, so we're good. Thanks for watching. That's a long video.